Okay, equations of tangent lines. There's a type of problem you're going to see throughout calculus, or at least throughout the first part of calculus when you're working with derivatives all the time. So I'm introducing this concept early because some classes do. But because, like, if you look on in the chapter about derivatives, we actually haven't gotten the power rule and chain rule and all that stuff, which you'll probably do before you find the equation of a tangent line. So for the purposes of this video, I'm just going to always give us the derivative so that I don't have to worry about whether you've already had that or not in class. But of course, if you want to find the derivative of a function in order to do this type of thing, you're going to have to know how to find the derivative usually. So the point is, I'm just going to take that for granted. And then also, I want to remind you, this is point slope form of a line, the equation of a line. I'm going to always use this because it's so much faster for the type of problem you have in calculus, where you have a point and a slope. If you're not familiar with this, go back to the video right before this one, which was a review of point slope form. It's only like 2 minutes long, super quick, but this formula will save you time on the test. And calculus tests tend to be very long, so if you can shave 15 seconds or a minute off of each problem, you're doing yourself a big favor. All right, so first problem. This is the most basic type, the most common type. They'll say, hey, find a line tangent to this thing. Now, if you recognize this, it's a parabola. So here's a parabola, and it's got a vertical shift of 2. So what they're saying is, there's a lot of tangent lines. Any given function has like infinity different tangent lines. Each point has a particular tangent, but as you work your way around that graph, you'll have all these different tangent lines, right? But they're saying, hey, we want the particular one that hits the graph at 1, 3. So that's a point right here or something. We don't even have to look at the graph. We just kind of know this is going to be a plug and chug situation. All right, so they've already given us a point, which is great. If you're plugging into point slope form and you have a point, that means the only thing you need to get is slope. That's what we use the derivative for. Now, if you know the power rule, you'll know that the derivative of this function, x squared plus 2, is just 2x. Or if you even use the limit definition, and it took you a long time, you figured out the derivative was 2x. So once we have that, we can just plug in x equals 1 to get the slope, because the slope is just going to equal y prime of the x value we're curious about, which is 1. And of course, we plug in 1 to 2x, we just get 2 times 1, which equals 2. All right, so now I have my slope and I had my point, so just plug into point slope form. Y minus the y coordinate is 3 equals the slope times x minus the x coordinate I have, which is 1. And we're done. Pretty sweet, right? And if you had graphed this, you would see that a slope of 2 is, it looks reasonable. That could be a slope of 2. We're definitely looking at a positive slope. Based on the graph, it's going up to the right. Therefore, it must be a positive slope, so it's not unbelievable that the slope is 2. That's enough of a, sort of cursory check to see if we're crazy or not. All right, find the tangent line to y equals square root of x at 4, 2. Once again, we've been given the point. And a second, we'll get in a slightly more difficult one where you're not given the point. But again, it's just still not a lot harder. So 4, 2 is our point. That's really great. We just need the slope. If I wanted to, I could even plug into the line right now, since I know enough stuff. Y minus 2 equals some slope times x minus 4. So you can see all I'm missing is the slope. That's what I'm going to get from y prime. So now, if you've had the power rule and some derivatives, you might be able to figure out that the derivative of square root of x is this hunk of junk. And we actually derived this using the limit definition in the previous chapter, which is a long and excruciating process. But hey, once you have the derivative, this problem's super easy. You just plug in 4, because what we need is y prime of the x value in this problem, which is 4. It's this puppy right here. So we're just going to plug in 4 to y prime to find out what the slope is at x equals 4. And you'll notice that there's no y's in the slope formula or the derivative. There's never a y over here. So you'll notice that the slope only matters. You only plug in x, never y. That's something that's a little bit interesting, but basically it's because it's a function, so there's only one slope. Anyway, you'll know, even though they gave you a point 4, 2, you only have to plug in the x coordinate to the derivative to find the slope. But once you got y prime of 4, note to self, if it's implicit differentiation, that might not be true, but 99% of the time it's true. All right, so y prime of 4 is going to be 1 over 2 times the square root of x, which is 4. So that's 1 over 2 times 2, which is 1/4. Awesome. All right, are we done? Oops, this is just the slope. We just have to plug that in for slope right here. So the slope of the equation at 4 is 1/4. Plug that in, and we're done. So you see the trend here? We just need a point on the line, and we need the slope, but the slope we're going to get by plugging into the derivative. All right, what if they don't give you a point? This is not a lot harder, but just slightly more confusing. Because, of course, it's really great when they give you a point. You just plug it right in the equation. But we don't have a point or a slope on this one. So we're going to have to do a little bit of extra work. First of all, y prime we already know to do, right? You notice they said find the line tangent to this function at x equals 3. At x equals 3. So that means we can just plug in 3 for x, right? Plug it in right there. So y prime of 3 is going to equal -2 times 3, which is -6. All right, so that's pretty cool. I've got my slope. But now, what about an x and y point? So if I try and plug in the equation right now, point slope, I'll get y minus a y coordinate, don't know what it is, equals the slope of -6 times x minus something. All right, so I'm missing the point. But how do I get a point on a function? Couldn't I just find any point I want? It's going to be 3 comma whatever y this is. So I just want f of 3, right? F of 3 is just the y coordinate. So it turns out to get a point, it's going to be 3 comma and then plug in 3 to the original function. Not the slope, not the derivative. If you want to know the actual point on the graph, you plug into the original function. So it's 3 minus 3 squared. You plug in 3, you get 3 minus 9, which is -6. All right, so by a complete coincidence, the slope and the y coordinate are the same. Anyway, so y minus a -6 is actually y plus 6, and then x minus 3. So we get y plus 6 equals -6 times x minus 3. Good stuff. Now naturally it could multiply this out and reduce stuff to give you slope-intercept form, but again, I would recommend just sticking with the point slope. All right, a hard one. Why is this hard? Oh, because they kind of gave us the slope in a backhanded way. Now, anytime anybody mentions a parallel line, just think to yourself, oh, they must have the same slope. So what this means is we want the equation of a line tangent to whatever, and we want its slope to be 2. So m equals 2. And that's kind of convenient because that means that we can this is what we're going to plug into the point slope form. The problem is, how the heck am I going to get a point to put in the point slope form? Because they haven't given me a point. They didn't even tell me the x value they want. That previous problem said, find the line tangent to whatever at x equals 3. We knew to plug in 3 to everything. But this time we haven't even gotten anything to plug in. But it turns out there's a catch here. Because they gave us the slope, we could say, you know what? We want the slope. We want 2x to equal 2 because we're looking for the point on the graph where the derivative 2x is 2 because the 2 is the slope we want for the tangent line. So at this point we've got an equation that we can solve for x. Divide both sides by 2, we get x equals 1. So it turns out that this was a really backhanded way. This question was like a really obscure, obfuscated way of telling you that we want a slope equal to 2 on our tangent line. And then we're going to have to solve for x by plugging in to the derivative. So crazy, kind of backwards thinking, but that's the trick. So if they ask for perpendicular or parallel, that means they're sort of telling you the slope, and then you've got to use the derivative equation to solve for what x should be. And x equals 1, oh, but look at that, we still don't have a point, right? We already have a slope, and we know x equals 1, but we don't have the point. How are we going to get the point? We know x equals 1. But what's the y-coordinate of this point that we want to plug into the tangent line equation? Well, we got to use the original function. Here is the original function, the line tangent to this thing. So to get the y-coordinate, we have to plug in 1 to this. 1 minus 2 is -1. Oh my goodness. All right, so at this point, I've got my point, and I got my slope. So I can do y minus a -1, so plus 1, equals 2 times x minus 1. All right, gnarly. Now your teacher might be able to cook up even weirder ways of sort of awkwardly giving you information, but ultimately every one of these questions boils down to finding a point and a slope that you can plug in the point slope form of the line. So just whatever weird word problem-y way they give you, just realize that's what you're trying to do, is find a single point, the slope at that point, so you can plug into the equation. Now in this one we did, they used the device of saying, hey, give us something parallel to this other line, so we knew the slope equals 2. They could also have said perpendicular. They could have told you they want it perpendicular to something, in which case I just want to remind you that the slope of the perpendicular line is the negative reciprocal. So if your original line was 2x minus 7, and they said, hey, we want the tangent line perpendicular to this line, we'd take our slope, we would flip it, so 1/2, and negate it. So that's just the negative reciprocal, and that's just to remind you that, hey, the perpendicular lines have negative reciprocal slopes. All right, good times, that's tangent lines. What makes these harder and harder in later chapters is that it'll be harder and harder to find the derivative, but ultimately you'll just be plugging in to the derivative, just like we did in these problems.